Hi guys, so in this video lecture we'll be uh, taking on some more examples on Haeckel rule, and so I'll be telling you some more important points. So let us compare the stability of these two compounds. I have an example in which we have to compare the stability of these two compounds, this one and this one. So let's call this as compound B and this is compound A, right? So in this case, as you can see that we have lone pairs on oxygen atoms, so these can actually involve in resonance, hence stability order is B is more stable than A. And if we talk about bond length of the double bond of the alkenes, then what would be the order of the bond length? As you can see that in the resonating structure it would have more single bond character. This would have a more single bond character here, unlike this bond which is permanently double bonded. So hence as you know that it is having sp2 character, this compound will be having sp2 character, but this compound in resonating structure would be have will have partial sp3 character. So in sp2 character we know that the bond length is shorter than the sp3 bond length, hence the bond length of B would also be greater than A, right? So when we talk about so let us talk about rotational barrier. Rotational barrier is directly proportional to the bond length or the double bond character. So let me write this, that rotation barrier is directly proportional to double bond character. Okay, so as sigma bond character increases, more rotation across the bond, more rotation. Okay, so in this case the rotation barrier, for if we compare the for these two compounds, rotation barrier will be, the order would be A is more than B. Why? Because the rotation barrier also B would be more than rotational barrier is the barrier, means it should not be easily rotated, right? So it is inversely proportional to the stability. So this would not be the order. B would be having more rotational barrier. Okay. I beg your pardon. A only would be having more rotational barrier than B, because A, it tends to be having more sp2 character or double bond character between the two carbon atoms. Okay, so let us take some more examples here on the aromaticity of certain compounds. So we have some example, like we need to comment on the aromaticity of this compound. Okay, so it is having 6 pi electrons, it is planar, it is cyclic, it is delocalized, the resonance will take part in covering all the carbon atoms, so hence it is aromatic, right? So now let us talk about perimeter resonance. Okay, so perimeter resonance is, if you look into the example of naphthalene, then we would have something like this carbon coming in, this double bond coming into this between these two carbon atoms. This will be going to this will be going to this will be shifting to this will be shifting to this. So in a sense, all of the carbon compounds are actually involved in the resonance, and the double bonds keep shifting on the boundaries of the compound, so it is called as perimeter resonance. Similarly, for this compound as well, we can have the perimeter resonance. Okay, let us mark the bonds. Okay, and it would be something like this, and what else? So I think it would be between this. If I have something like this, then for filling the valencies I need to put something in the middle, and again I have to do the same for this ring. Okay, so now in this thing perimeter resonance is working, but the perimeter resonance is not involving this middle pi bond. No involvement in perimeter resonance, because in perimeter resonance we look at the facing carbons of the compound, not the intermediary carbon atoms like this one. Okay, not involved in perimeter resonance. So I hope you get the point of the perimeter resonance concept. So now we will be comparing rate of reaction. Okay, so let us first discuss the rate of reaction of certain compounds with AgNO3. Okay, so we have something like this, wherein we have a reaction like this, wherein there is a compound RCl, organic compound RCl, and there is an inorganic compound AgNO3. So what happens is this R actually attacks on the AgNO3 inorganic compound, as a result of which we get R plus NO3 minus and AgCl salt is formed. Okay, so this R plus C NO3 minus, for the formation of this, the rate of reaction actually depends on the stability of the carbocation. Okay, so more stable the carbocation, more is its reactivity. We'll write it so that you remember. More stable the carbocation, more is the rate of reaction, or ROR. Okay, so let me take some example on the same. If I have something like then would it react more easily with AgNO3 or this one? This compound. So for the reaction with the AgNO3, we just need to compare the stability of the carbocations formed by replacing Br with positive sign here, and same with replacing Br with positive sign here, which is the products. We are just talking about these products, right? So if we compare the stability of the two, both are involved in resonance, no doubt about it. So we'll not be taking, we'll be comparing them on the base of the type, whether they are aromatic, anti-aromatic, or non-aromatic. So for this case, we have 4 n pi electrons. It is planar, it is cyclic, it is delocalized. Same for this thing, we have 6 pi electrons. It is planar, it is cyclic, it is delocalized, but this is aromatic, this is anti-aromatic. Hence, the rate of reaction would be this one for reaction with AgNO3. Okay. Okay, so one more important point I just would like to tell you here now is, suppose we have something like uh, we need to actually identify the stability order of this ring with this compound with this compound. So what would be the stability order? Here you can see that it is having a resonance in it, not involving the positive, but obviously phenyl ring won't be giving, phenyl ring will be taking part in the resonance with the positive bonded carbon atom here. So it is having resonance structure, but it is not. But on the other hand, it would have some phenomena which is called as dancing resonance. So what is dancing resonance? Dancing resonance is nothing but a concept defined to suit these type of cases, wherein what happens actually is we have the resonance take place in such a form that we have positive sign here. So this bond between this carbon atom and this carbon atom is broken and is given to satisfy the positive carbon atom or carbocation. So what happens is we get something like this. Okay, so in this case we can see that the ring strain of 60 degree is broken into a free chain compound. Hence, due to the breaking up of this cyclic ring because of dancing resonance, this is more stable than positive charge over carbon atom attached to a phenyl ring. Okay, so this is an important exception to be remembered. So I'm just write exception. You will find a lot of exceptions when you study in organic chemistry, so stay tuned. Okay, so just remember this exception by heart. It was asked in many of the previous examination papers and is in more likelihood to be asked in subsequent years as well. Okay, so with this we end this lecture, and in the next lecture we will be dealing on with comparating rate of reaction with AgNO3 of several other compounds. Till then, good luck and goodbye.